Yeah. Now, what I will do is probability of success is 0.8, which means 1 minus p is 0.2, right? I got, say, how many patients? I got, let's take a small number. I got 6 patients. So n is equal to 6 who have PTSD, and I send all of them to EMDR. Okay? So I can work out probability that X takes a value 0, none of them are cured by using EMDR, is 6C0 0.8 raised to 0 and 0.2 raised to 6, right? 6 minus 0 is 6, right? So let's quickly work it out. 0.6 is the 0.8 is the probability of success, and we are interested in 0 successes. 0.2 is the probability of failure, and we are interested in 6 failures. X is equal to 0, size is equal to 6, probability is 0.8, right?
Yes.
So this turns out to be 0.00064, right? Right? The probability that it will be 1 is 0.00, so probability that X takes a value 1 is equal to 6C1 0.8 raised to 1 0.2 raised to 5 is equal to 001536, 0.001536.
So
P is equal to X, X is equal to 2 is equal to, yes.
sir, why would we take the NCR formula? Because the sequence won't be important in this case.
That is why. That is why. Okay, I answer this question later on. Let's finish this exercise. 0.1536, 0.01536. X is equal to 3 is equal to 0.819, 0.819. 4 successes is 2457. X is equal to 4 is 0.2457, and X is equal to 5 is 3932. And X is equal to 6 is 2621. You can add it. This is to add up to. This is to add up to 1. entire of the sample space is covered. So what we have done, now I can actually do a small thing, and this is x is equal to x, this is p of x, right? Okay, or yeah, fine, and this is say 0.5, this is 0, and this is say 1. So x takes a value 0, 1, 2, 3, 4, 5, and 6. Probability of x taking a value 0 is extremely small. Probability of x taking a value is slightly more than it. 2 taking a value is slightly more than 0.1. 3 is 2, 4 is somewhere here. So this is the probability of 2, 4. 4 is 3, 9, so somewhere here, up to say 0.4. Then 3, 9. So, oh, it's 2, 4. 4 is 2, 4. 3 is 0.8. Yeah, so 3 is somewhere here. 4 is somewhere here. 5 is 3, 9. And 6 is 2, 6. Okay, this is my distribution. So this is how the distribution would look like if x is equal to x is equal to whatever 1 to 0 to 6, p is 0.8, and if I am doing binomial, then this is how my distribution would look like. Okay, so this is my binomial distribution, if I have to say. And you would understand that I am drawing separate bars because it's not a continuous variable, it's a discrete variable. So there's nothing in between 1 and 2, 2 and 3. Otherwise, in continuous, I draw a continuous curves like kind of distribution. So this is how a distribution I would draw if it is continuous. This is not a continuous distribution, so not drawing it continuous. So this is my binomial distribution function. Distribution. This is how it would look like, right? And this is how I would compute probability of each of the outcome associated with my binomial distribution function. The mean of the or expectation of binomial, expectation x for x follows binomial is NP. NP is the mean of the binomial function, and NPQ is the variance of the binomial function, binomial distribution. So NPQ would be the variance function. You know, NCX, P raised to x, Q raised to n minus x. Okay, you are asking why are we putting it? Perhaps the big exercise that we did of selecting 10 out of 32, we need NCX because we want all possible sequences. We are not interested in, see, when I'm saying that one person gets cured out of 6, I'm not just interested in the first person. It could be second, first, second, third, fourth, fifth, sixth. So I'm interested in any one, not a specific sequence. First gets cured. First gets cured is P raised to 1, Q raised to n minus x, right? That is just one sequence. So I need to add up all these sequences. For those many times, one would occur. One would occur 6 different ways. First position, second position, third position, fourth position, fifth position, sixth position, right? So how do I know it? 6C1. So I need 6C1. That is NCX. I need NCX.
Yeah. So if the n would have been 10, so the highest probability would come at the value of 8, right?
That depends on probability of success.
Yes. So the probability of success if it's 8 and
Perhaps.
the is 10.
Perhaps. Let's do it.
Because probably rate like 10 and the highest probability, and because it's
Probability is 8, total we take 10. It's 0.3 if you do it that way. and if we take 7, it's 0.20, 9, it's 0.26. So highest would be at 8.
8, right?
Yeah. Logically, it should be at 8. Now, the whole point is, how to do it in R. Okay? To do this in R, there's a very simple function, d binom. Okay? D binom. So, d binom, you will have to write the x that you need to write, x, then n, and then p, right? So what I'm actually writing for this example is d binom, say 3 successes, so 3 people are cured out of 6, and probability of people getting cured is 0.8, and I get the probability in R. So you type this and you get it. In R, you can write d binom. Similarly, you can write R binom, Q binom, and P binom. See, a departure from distributions to the bit of an R exercise. In R, distributions can be like you can get 3 different things for a distribution. Say binom. Binom is for binomial. So you get d binom, p binom, q binom, and R binom. Okay? So suppose if I am writing, instead of d binom, I am writing p binom, then I will have to write q, the quantile at which I want it, and then I will write the size and the probability. Size is n and probability is p, right? D binom we already know. So this will give me, for this quantile, the probability. Okay? So it's a probability function. Q binom would give me, if I write Q, size and probability, then it would give me P and Q are opposite to each other. I need to write probability for a given size, probability and given size, so that I get the Q. Right? Yes. I get the Q. So this is how I would perhaps write P binom, Q binom, and D binom. R binom would help me in generating the data. So in R binom, I will have to give the size for which I want the data, probability of getting that, that is sample size, P I will have to write, and what else? N, X and T. N, X and T. Right? N, X and T. So I get this. So actually in R, for all distributions, you can get all these 4 functions. Okay? So for normal, I have norm, right? So I get something like d norm, and I have to specify the parameters for the d norm, and I get d norm. So I also get q norm, and I specify the parameters for q norm, and I get it. So for each of the distribution, so for example for Poisson, I write d-Poise, and I get density of the Poisson distribution, right? So this is a simple thing in R which you can do, and do this much faster. I recommend that you use your own functions than depending on R's functions, because that will help you develop some proficiency with R. I don't know how much time you're spending with your studies as of now, but start spending sizable amount of time in your studies, because there's a lot of things that you need to learn, right? Well, now let's look at Poisson random variable. Okay. Poisson random variable has a following distribution function. Before we go to Poisson random variable, let me very good. Let's now look at some interesting transformations of binomials. Okay, I give this example very often. Now I'm getting scared with this example as I keep on giving it very frequently, but well, I still give it. My hometown is Pune, so I come from Pune. I stay in Bombay, and there are many times I go back to my hometown, stay there for a day or two, come back to this lovely city again. So there's this highway which connects these two cities called as Pune-Mumbai Expressway. Right? It starts from Panvel, it ends at Talegaon in Pune. Okay. The point at which it ends is a beautiful nursery on both the sides. I visit them very frequently. When I travel on this road, and particularly recently, I have realized that people have started driving not so well. Earlier people used to give signals when they were going left and right, because people generally